Hey everyone, thank you for coming to my talk, Securing the Pipeline, Protecting Self-Hosted GitHub Runners, and probably your Actions Pipeline secrets as well. So, about me, my name is Adnan Khan. I'm a lead security engineer at Praetorian. I primarily work on Praetorian's red team, but I also do some web application security assessments as well. In my past life, I was a software engineer, and as a result, I'm intimately familiar with the conflict that comes between the need to get stuff done and the need to also not leave a lot of vulnerabilities along with that process. So I was a speaker at ShmooCon 2023 along with two of my colleagues, presenting an offensive-focused talk called Phantom of the Pipeline, Abusing Self-Hosted CI/CD Runners, focusing mostly on GitHub, and we open-sourced a tool called GitHub Attack Toolkit, Gato for short, and the mascot's a cat. You can see the play on words there. And this is my second conference talk. And I'm based in Baltimore, Maryland now, but originally I'm from the East Bay area, so it's kind of nice to be on some familiar soil. So why this talk? Well, because DevOps. So DevOps, there's a lot of moving parts and a lot of places where things can go wrong. And securing DevOps environments is pretty hard, and I've seen that personally on a lot of red team engagements targeting organizations that use GitHub Actions. And really, there's a lot of chaos. There's often a lot of repositories. Some organizations, developers are able to create their own repos. You might have people creating individual .files repositories. Things can be quite all over the place. There are API tokens that might be added as repo secrets, as organization secrets, and some organizations will use self-hosted runners for deployment or other integration where they might not want to run it on GitHub's Azure-hosted runners. And compounding that, there's a lot of permissions that can sometimes allow developers to make mistakes and not really know what they're allowing someone to do if there is a compromise. So the way this presentation is going to be structured is I'm going to go give a quick primer on GitHub Actions CI/CD and some of the specifics that apply to that product. Then I'm going to cover some risks and attacks that exist, as well as some attacks that I've personally conducted on red teams or some colleagues have conducted, and how certain types of attacks can be detected and perhaps even prevented, and then talk about some future considerations, and if there's time, open it up for some questions. So GitHub Actions is a little bit unique with how it plays into the larger part with GitHub. So since GitHub started as a company focused on open source projects and smaller teams, and recently after the acquisition, well, it's been a while now, after the acquisition by Microsoft, it's continuously moving towards becoming an enterprise SaaS platform. So there's a bit of a conflict there. The build agents themselves for GitHub Actions, they can be self-hosted or hosted by GitHub. And the secrets which can be used for GitHub Actions can be supplied at a per repository or per organization level. So there's a lot of places where secrets could be left and then subsequently compromised. And I also want to touch on some other CI/CD solutions that are similar. There are different attack paths that target them. There are issues there with some of these other services as well. So it's not just that I'm picking on GitHub. So the way self-hosted runners function on GitHub is that there is a .NET Core application, which is the GitHub Actions Runner Agent, and that supports a number of different operating systems. And that particular runner can then be attached at a per repository level, per organization level, or a per enterprise level. And at each of these levels, it essentially functions as a worker pool. So workflow jobs will execute, and a runner will pick up the job, complete it, and then that runner will be available again and return to the pool. So the problem is that the default configuration leaves a lot of open attack opportunities for an attacker, mainly because the runner is not ephemeral and there's no isolation between builds. So, and I'm going to really touch on that later in the talk. I also want to introduce GitHub personal access tokens. So these are API tokens that are associated with user accounts. So GitHub is unique because a lot of times organizations will have developers join their personal GitHub accounts that they might also use for side projects to an organization, and that will grant them access to their employers' repositories and other assets. But personal access tokens belong to the account itself. So someone could create a token for personal usage, but if the organization is not configured properly, that token could provide access to a lot more. And these tokens can also be used for traditional command line Git operations. So that's your standard cloning or pushing code. That can be disabled, and I'll touch into cover that a little bit later as well. Finally, the way that these tokens work is OAuth scopes. So the key thing about these scopes are for classic tokens is that they really just determine what API operations that token is allowed to use. Just because the scope is present doesn't mean a user can actually do it, because there are certain API operations that require the user to also be an administrator in an organization. So creating a user token for a member that has an org admin scope doesn't really allow that, but I do want to cover how these tokens work, because that also plays into where some of the over provisioning happens. So there are two types of tokens. Until last fall, there were just classic GitHub personal access tokens. Since about 2021, they've just started with the GHP_string, and that denotes a GitHub personal access token. But with fine-grained personal access tokens, which start with a GitHub_pat string, they allow, obviously, as the name suggests, finer-grained access controls. However, they're like with anything that requires more fine-grained control, it requires more upfront effort to provision them. So people often take the short way. And finally, going into GitHub's API, GitHub has a very extensive API that supports almost any operation that you could probably think of wanting to do with GitHub. There's an API endpoint for it. There are some, like for example, API endpoint operations that allow you to directly interact with low-level Git blobs. Higher level than that, there's the ability to commit single files or pull single files from a repo using just that API. So there's a lot of potential for enumeration and attack using just a token there. And also, there's some interesting things that you can do, like if an organization restricts Git operations like clones or pushes to just users that have an authorized SSH key, using the repository contents API to push single files or clone single files will allow you to bypass that restriction and get specific files from a repo. And you can also list it. So it's slower, but you can get the same thing or do the same thing there. So that's a little interesting thing. Finally, going into the gaps related to the GitHub API, the vast majority of read requests are not logged. So the problem here is that attacker that compromises a developer token can enumerate everything they need to before they generate a single event that would trigger a detection or compromise and actually start an incident response process. There are some exceptions, like the one where if you just download a zip file from a repository, the associated API request is logged, as is the zip download operation. There is some good news, though. Just as of February of this year, GitHub has finally released a private beta feature where an enterprise can actually get a full fire hose of all the REST API events hitting their organization's assets. So things are moving in the right direction, but it'll be quite some time before this is made public beta and finally adopted and people actually write detections based on these events. And then GitHub Actions secrets. So this is something that is documented by GitHub. It's not something unknown, but some potentially people might not actually know this, and because of how when you add a secret to a repository, you need to be an administrator, and to list it from the GUI, you need to be an administrator. However, any user that can just push code to a repository can execute GitHub Actions workflows that can access every single repository secret that's attached, or even organization-wide secrets that are in the default group and therefore are accessible to all repositories. So there's that gap between who can look and monitor secrets from the GUI and then who can actually utilize them or hit the API endpoint to list secrets, which again also requires the just write access to a repo as a normal collaborator. Okay, so now that I've introduced GitHub Actions CI/CD at a higher level, why would an attacker want to target self-hosted runners? Well, a lot of reasons. The traditional thing when you think about GitHub is obviously source code theft. That's a concern for a lot of organizations and one you obviously commonly think of, but there's potential for taking secrets and then moving laterally to cloud or accounts. There's artifact poisoning and trying to get malicious packages pushed where other people, other systems, other clients can pull them and now get malware on their systems. And finally, as we've all probably heard about the recent 3CX hack, the potential for supply chain attacks. And if you're an attacker that wants to conduct supply chain attacks, attacking an organization's GitHub is probably the best place to hit if you actually want to be successful. And finally, there's the risk if an organization is using self-hosted runners for broader network intrusion and lateral movement if they are not properly secured. The kind of attacks that an attacker can conduct against self-hosted runners, so if runners aren't configured properly, then malicious code that started off from one build can persist beyond that build and get secrets that are used from other builds, even if that attacker that kicked off the initial workflow might not have had access to those specific secrets that they're now seeking to exfiltrate. There's the ability to conduct supply chain attacks by sitting on a runner and modifying code associated with other builds as they check out code before compilation or pushing to an artifact repository. And finally, if you have just a compromised developer access token, an attacker can, knowing nothing else about what that token has access to, get a foothold within an organization's network by using that token to learn about the organization associated with and then conduct an attack. At a high level, this is kind of how the external to internal attack looks. There's a compromised access token. An attacker will push a malicious workflow to a code repository that is configured to have actions run on self-hosted runners. A self-hosted runner will then pick up the job, only communicating there with GitHub. And now that attacker has code running within a corporate network, again, given that the runner isn't properly configured. And finally, you also, at least personally on red teams, have seen that deployment of EDR and antivirus solutions on self-hosted runners is a bit rare. We've seen it, but we've also seen absolutely nothing. So you can just drop unobfuscated malware and you're good to go. That's not good. So is this particular kind of attack happening? Well, not from what I know, not yet. Specifically looking at GitHub self-hosted runners and conducting an attack and gaining access to network systems and conducting supply chain attacks. So not yet. However, really there's been a lack of tooling to target these self-hosted runners, as well as there's not been that much documentation and tradecraft techniques for an attacker to get a personal access token and don't know what they need to do with it. And however, on red teams that Praetorian has operated on, we've yet to see a client that has had a secure self-hosted runner implementation if they're using GitHub. In every single case that we've encountered, that compromised developer access has allowed us to move laterally, escalate privileges, get prod AWS, prod GCP accounts. It's been access to crown jewels in every single case when we've seen organizations use GitHub and GitHub Actions. We also haven't been detected while doing any of these attacks. So this is a real-world attack that was conducted as part of one of our red team engagements last summer. And the way it worked was we had access to, we were from an external standpoint. We used another social engineering attack to essentially gain access to logs, where one of them had a personal access token. So I'm going to start there. What we did was we thoroughly enumerated what that token had access to and just using GitHub's API, because again, we didn't have access to that organization on github.com. We couldn't just open up a browser and do that. Then once we learned that they were using self-hosted runners, we created and pushed a malicious workflow to a repository. We set that workflow to run on self-hosted runners via a tag. That queued up the job. A self-hosted runner picked up the workflow, checked out the code, and we were now on a self-hosted runner. And that one had Docker enabled. So what we did was we just spun up a detached Docker container that pulled down an implant, and now we had persistence within their network connecting back to our C2. That eventually then let us conduct privilege escalation lateral movement, and we gained very high level privileges within that organization from that purely external standpoint and compromise access token. Okay. All right, and this is a similar attack path, but the key difference here is instead of the goal being just attacks on other systems, is where we started off with, again, that compromised access token. In this case, it was a penetration test, so we had that developer access to start with, but very low privileged. We pushed a malicious workflow, but now instead of we still implanted the runner, but now we just sat on that runner and waited. Now, again, this is a self-hosted runner, so our build is the build that we kicked off is finished. There's another, it's now able to execute other builds. So in this case, there's a sensitive infrastructure repository where there are secrets in use that have high privileges. So here comes an infrastructure developer, they commit a code change, and now they push a change to run, say, integration tests. Now, their workflow is pushed, that self-hosted runner picks up the job, and since it uses secrets, and in this case, it was secrets used in a shell script defined in the workflow, which essentially on GitHub means it's just written out of the file system with the plain text secret. Since we're on that runner, we watch the file system, the working directory of the self-hosted runner, we now have access to those plain text secrets. And we get the secret and we exfiltrate it. So and again, no detection, and the developer has no idea that something bad happened because the build succeeded properly, nothing bad happened from their perspective. So this leads to risks and that are present, and then some of the mitigations that can be used to fix a lot of these problems. So for like footholds, obviously you have making sure that there's network segmentation, monitoring builds. For secrets, there's access control lists and auditing, compromised personal access tokens, using fine-grained tokens, so it's like your perimeter security, educating developers and not over-provisioning access tokens, detection engineering, and generally for the build modification, just having per-job ephemeral runners kind of takes that entire attack class out of the picture. And for malware deployment, looking at network segmentations and on self-hosted runner mitigations. And really, to properly secure an organization's self-hosted runners and actions pipelines against sophisticated attackers really requires a layered approach at every kind of step of being the external perimeter. What do you do if something is compromised, and properly responding to a compromise if it does happen. So for looking at perimeter security, one thing that we've seen some organizations do, but some also don't, is with GitHub, you can require SAML SSO. And what this basically does is when a developer creates a personal access token, they will now need to specifically authorize that token to be able to access organization resources. So if you have this enabled in an organization, it prevents the situation where a developer creates a token for personal usage, but it also has access to organization's resources. Requiring SSH authentication for Git operations can also be helpful. It could prevent an attacker that just gets a token and now it can clone every single repo. So if, say, cloning repos isn't a part of a normal workflow, then maybe an organization can disable the ability to do git clone, git push operations with just a personal access token. And there's also cases where there's certain defaults that are not enabled that organizations can enable to get better visibility into actions that are happening. IP logging is an example of that, and I'll show where you need to go to enable that setting and why it's off by default. And keeping in mind that point I touched on earlier, where if someone has a write access to a repo, they can access every single secret. So having a secret in a repo and having someone that can write to it, it's basically the same as giving them access to that plaintext secret. There's just a trivial exercise in pushing a workflow in between them and getting the plaintext value. So it's important to understand what that means and limit secrets to only those who have really a need to know of that plaintext value. So this is like the IP logging setting, which is disabled by default. I believe it's for privacy reasons, and it's in public beta that it's disabled by default. But if you have GitHub Enterprise and you have the audit log, it's probably smart to enable this, because then you can have GeoIP-based detections on potential malicious activity. And so classic tokens, as I mentioned earlier, these are tied to an individual user, and then those scopes, like say repo or workflow. So a repo scope is what would be needed to clone repositories. Workflow scope is what would be needed to run GitHub Actions workflows. Those are all assigned at creation time. And with how classic tokens work, there's a lot of API endpoints that allow you to learn about what they have access to. So you can use a token to query what authenticated user it belongs to, what organizations that user is a member of, what repositories within that organization that user has access to. So you see where I'm going, where you eventually can map out everything you have access to and build an attack plan. So to address this, there is an option now to disable classic tokens completely, but it's all or nothing. So for an organization that might be new to GitHub Actions and personal access tokens are not ingrained in your current workflows, perhaps taking those out of the equation now and dealing with the consequences is better than, say, years down the road, where now you have a lot of tech debt, and going back and changing all those processes to not use classic tokens is so much work. So guess what? Priorities, it falls down the totem pole of priorities and it never happens. So that's something that to consider if your organization needs tokens as part of the normal workflow. And again, that SAML SSO feature, again, this all requires the GitHub Enterprise plan, so which is their most expensive plan, but really the Teams plan is, I would say right now, impossible to secure properly against a sophisticated attacker. But making sure that that SAML SSO setting is enabled. So to address some of the issues with classic tokens, organizations can use fine-grained personal access tokens. And as the name suggests, it allows you to have fine-grained controls over what repository the token can access and what specific kinds of operations that token can be used to perform. And beyond just the limitation of the access, organizations themselves can configure it so that if a fine-grained token is created and a user wants to authorize to an organization, the organization can approve it before it has that access. That's not the case with classic tokens. Classic tokens, developers authorize them, even if there's SSO requirement for it. Developers authorize it, and it's enabled. The organizations can't go and stop that before it happens. They can only do it after. And it's just harder for attackers to use that and learn what it can access and conduct these attacks that I mentioned earlier. So alerting on that for classic tokens, organizations can monitor when they're authorized and what scopes that token has access to. So an organization could monitor the organization credential grant log event and then fire off potentially different APIs operations against GitHub's API to list tokens that have been previously granted and even revoke them. So that could be made part of like an incident response playbook where if unusual activities detected with the user, an organization can quickly list and revoke tokens that have been created associated with that user. And that API response does display the scopes, so it could also be used to detect over-provisioned tokens. So it might not be a critical alert, but it might be something where someone can message a developer, say, hey, this token is over-provisioned. Can you see if you can configure provision in a more secure manner? So something like this could help organizations move towards a better security posture with the kind of tokens that their developers are provisioning. So now everything I've talked about so far is looking at preventing an attacker from getting access. Now, say an attacker does get inside an organization with the right kind of access token and starts conducting these workflow attacks to attack self-hosted runners as well as try to steal secrets. Well, is there anything that can be done? Yeah, there's a couple things. So again, I keep stating this, but this is important. But since any user that has write access can get secrets via malicious GitHub Actions workflows. So I want to emphasize, I've seen a lot of organizations that use branch restrictions. So there might be a workflow that runs for the main branch and has a runs on main branch in the workflow YAML file as if that restricts access to the secret. It doesn't. So any user can just that has write access can create a feature branch and push a new workflow that they control entirely, which is say, take the secret, base64 it, send it off to a attacker server. Congratulations, you now have the plain text secret value. So that is important to look at getting who has access to secrets to make sure you limit that exposure from the beginning. And the way that you can do this in a programmatic manner, you could probably write a quick Python script to do this, is essentially for each repository in a given GitHub organization, make a query to the secrets API endpoint, which essentially lists all of the GitHub Actions secrets attached to that repository, and then follow that up if there is at least one secret, because otherwise there is no need to do that subsequent operation. But if there is one secret, then now you can list every collaborator that has the push permission, and that resulting mapping, that's your list of users that has access to all the repository secrets for a given repository. I do want to note there is another way that you can use secrets, and that's GitHub environment secrets, and there's a little bit more security there, but some of the similar problems exist, but I don't want to spend too much time on that, but that is another thing that organizations consider is environments and using deployment secrets there. So I want to take a quick step back to talk about SALSA, and this is a framework for software supply chain security, and actually had to go up these slides because they just released their version 1.0 on the 19th. So and obviously someone could spend a lot of time talking about SALSA, and probably a whole talk, so I'm just going to quickly talk about specific points that pertain to the build step. And this is a very new framework, but essentially for build, there's 4 levels, starting from build L0 to build L3. And build L0, obviously, that's nothing, no security. Build L1, you have automated builds, so that's just using something like GitHub Actions to run builds. And then there's that provenance of what led to that build and and tying that to the artifact. Build L2, essentially just take that provenance, have that on a hosted build service, and it's signed. But again, if you're really interested in that, definitely read up on SALSA. I don't want to spend too much time on that, but the thing that applies to self-hosted runner type attacks is build L3, build service hardening. And what that is that for an organization to comply with SALSA build L3, they need to be using isolated builds. That means that each build is isolated from the next build, so there's no intra-build interaction, and that there's nothing in the build system's control plane that can allow a build to interact with the subsequent build. Like say there's a cache and one build can poison the cache and the next build now uses a poisoned tool. So that would be something that shouldn't happen if an organization wants to comply with SALSA L3. There's also protecting the signing secrets used for the sign the provenance, but I'm not going to spend time there. Another risk, so if a self-hosted runner is used, you probably have antivirus or EDR present on these runners. Attackers shouldn't just be able to go and run a malicious ELF file in the background and that's unobfuscated. Like they should have something to at least catch the less sophisticated attackers. There are, if you're using containers for self-hosted runners, there's a lot of EDR products and vendors that offer solutions there, but I'm not going to name any, but there's plenty of them out there. So there's also a risk of code modification. And this kind of touches on that supply chain attack that an attacker might want to conduct in a very stealthy and hard to detect manner. So what'll happen in this case is you have a self-hosted runner and it's not ephemeral. So attacker will create a malicious workflow, push it, and now start a build. That build starts that background process and the build ends. Runner is now ready to pick up other tasks. That background process now continues to run. A legitimate build comes out, checks out code. All right, let's get to that step here. That legitimate process will then check out code, and the malicious project might already know which build it's targeting. So it looks for that file, swaps it out with a malicious file that contains a backdoor, and now that pipeline continues with its normal steps. It compiles it and publishes it, but now you have a backdoored artifact which is linked to a legitimate original commit. So the only way in this case would be to go and reverse engineer that final build artifact to find out that there was some modification made, because otherwise the original commit checks out as legitimate and it's all signed properly because it's following the normal pipeline in every other way. So that's where an attacker could obviously conduct that 3CX style attack if they wanted to against organizations that use GitHub Actions and non-ephemeral self-hosted runners. So the other risk is kind of that tool or cache poisoning, and the way an attacker, this is a more like a theoretical example where the build will check if a tool is installed, and if it is, use it, but if not, go and install it. So in this case, if it's a non-ephemeral runner, that malicious initial workflow could just install the tool, and then that second build will just say, okay, the tool's already installed, I'm going to use it, and now your supply chain is compromised. So another way an attacker could accomplish that same goal of modifying code, but this is just presents in a different manner. All right, and then there is also the risk of stealing secrets from subsequent builds. So that this is where you might have a container that's isolated from the network. So there's no risk of lateral movement into other systems. But if that container is maybe not ephemeral, maybe if it's only rotated every 24 hours, then attacker can start a background process. And if they can escalate to root, then they can just dump the memory of the GitHub Actions agent and get all the secrets that are sent associated with subsequent builds, or use the technique of dumping secrets from shell scripts in the workflow. In that case, it's just looking at files on a file system, maybe setting like an iNotify watch and just pulling the shell scripts when they appear. To address those risks, and this aligns with SALSA build L3, is using runners that have an isolated and ephemeral environment. So it'll completely eliminate all of the risks associated with that build time code modification, stealing of secrets via monitoring, stealing of secrets via dumping memory. But do you understand that in some organizations, it might not really be possible, or it might be possible, but the time and budget constraints prevent moving away from self-hosted runners to a proper ephemeral setup. There are other mitigations and defensive controls, some I've outlined before, like EDR, that will then be very critical. And if you are trying to move towards setting up ephemeral runners, I want to note that the GitHub Actions agent supports self-hosted running in a self-hosted manner, but really that just means that you pass the self-hosted flag, and as soon as it runs the job, it deregisters itself. But that infrastructure, that's up to organizations to manage. Thankfully, GitHub does recommend 2 open source frameworks that handle all of the provisioning and deprovisioning configuration. And I'll link both of these here. And also, I have tweeted out the slides for this. So if any of these links or anything wants to see, I can make sure to, because I know I have a lot of content here. Okay, so touching on that risk of internal network access and moving to other systems. Now, this is one where an attacker could do on a ephemeral runner, given that network controls aren't set up properly. So per GitHub's documentation, a single GitHub Actions workflow can run for up to 35 days. That's quite a while for a build. And that's also quite a while for an attacker to do bad things in your network. You definitely don't want that in your network for 35 days. So the way to kind of handle this is looking at standard network segmentation type controls, making sure these runners have limited internal access. And if there is a need for, say, a runner that has more extensive access, then look at limiting those runners to repository level self-hosted runners, and then auditing that create workflow run log event to make sure that no one that shouldn't be running workflows is running workflows on those runners. To kind of handle the case where there's a build that's lasting for days and days, and that's an attacker, basically the run is just running it like an implant, there really isn't a way to, at an organization scale, to track the duration of builds on given a single self-hosted runner. So the way to kind of handle this one would be look at taking the logs off of the self-hosted runner itself. So there's a directory, the diagnostics directory where the runner application is installed, and there'll just be log files there. So setting up some tooling on the runner itself to take those files and send them off for perhaps some processing and then ingestion to a seam. So that could help keep an overwatch of what's running on a self-hosted runner and how long these builds have been running. To detect the case where a run has forked off a process, so this runner tracking ID environment variable essentially for GitHub Actions it's a feature where if a process is running, if that's not set to 0, then once the job completes, the Actions agent will reap any processes that it's started. So if someone starts a process and sets that runner tracking ID variable to 0, then that backgrounded process will not be terminated after the build finishes. Again, this is on a non-ephemeral runner. So perhaps doing something where you check processes on the runner by the GitHub Actions user and see if that variable is set to 0. There may be some legitimate cases for this, but if you don't have any legitimate cases for this, seeing that would be an immediate indication of odd or malicious activity. So raise an alert and investigate it. Going into GitHub's audit log, I mentioned earlier in the talk that there's a couple gaps that exist. So there's a few of these audit log events that can only be pulled in via the REST API, meaning if you have it set up to just stream, it's not going to be included by default. So, and these are the audit log events like when associated with the creation of a workflow, as well as Git operations, so Git clones or push operations associated with an organization. Those are not automatically present. So that's important to ingest those, and if you do need those to build certain detections. And if you have that default setting of IP logging changed, then perhaps looking at GeoIP-based detections for activity associated with users. So if you know where your user is and suddenly you have a bunch of a cluster of events coming from Russia, that's probably not good. So that's where you could start building some detections for malicious activities. And this is doubly more so for events associated with critical repositories. And using the GitHub API, you can actually filter audit log events associated with a given repository. So for maybe critical info repos, watch those very closely. Here's something that I've not seen personally, but would be really cool for someone to start implementing, is by adding a honeypot repository within a GitHub organization. So a way I could see someone going about this is making a repo that every user, every developer can have, every developer can write to, name it something that seems like it's valuable, add some juicy repository secrets, add a self-hosted runner, make sure it's isolated, so make sure your honeypot doesn't end up actually causing a breach. Don't want that. And then closely monitor the API. So this setup can allow someone to pick up events associated with malicious activity. And here's something, again, and I recognize that detection engineering is a pretty complex thing, and it's not just it's not a one-size-fits-all approach for every organization, but I hope something like this could be a start for organizations to develop detections and start treating GitHub Actions and associated log events just as they would AWS IAM events, as an example. So the kind of a cycle that could work for GitHub Actions is taking the audit logs, streaming and REST API, filtering suspicious events, and tailoring that to how your organization works, because every organization is going to have a different baseline associated based on how developers work. But looking at things like, if you have a bot user and it's only doing like comment triage, why you're seeing events like associated with other events. So that's a good place to start, because if a lot of times the tokens that are compromised could be bot accounts. Looking again, GeoIPs, access to certain repos, then you can move on to enriching these events. So for workflows, any malicious workflow, even if the actions that happen later don't have a good trace, it still starts off with that workflow YAML file that's associated with the commit. So, because that would need to be in a repo for it to actually run a workflow. So having any events associated with GitHub Actions workflows, it'd be good to pull the workflow file and package that along with the event. So if someone does need to look at it for manual triage, that workflow's right there. Because if it's, say, pulling down a shell script from an unknown domain, that's probably bad, and good thing to alert on and start a potential incident response process. And then these are the kind of API endpoints that you would use from GitHub's API to enrich workflow events. So you can get workflow runs and get the workflow associated with a suspicious created workflow run log event, take the SHA of the commit and the path, and then use another API request to get the workflow YAML file itself. So now you have the workflow YAML file associated with the potentially malicious event, and it's right there. You don't have to go hunt down and spend 20 minutes figuring out where this workflow file lives. It's part of a triage process. And if you did that and you saw something like this would obviously be clear indication of malicious activity. And if an organization can detect that just the fact that a workflow was executed that did this, then already they're more secure than most organizations, at least based on what we've seen on red teams with organizations that use GitHub Actions. So to conclude, we're really starting to see developer compromises become the source of really impactful breaches. Obviously, you had Circle CI back in December, and that one I really believe that if the attacker knew what they had, they probably could have done a lot more damage to some of their clients. LastPass, that started from a developer compromise. And so to protect your organization's GitHub Actions CI/CD, like I had mentioned earlier, there's that layered approach. You want to apply the principle of least privilege, both the repository secrets as well as how you have your self-hosted runners configured. You want to have secure runner implementation in that you are using ephemeral runners if you can at all possibly do that. And if you're not, making sure you have proper EDR protections. And honestly, even if you have ephemeral runners, you should probably have EDR AV protections on it. And then looking at starting detection engineering, pulling in log events that could indicate malicious activity, and starting there and trying to get something that's better than what it is right now with a lot of organizations that use GitHub Actions. And just some food for thought for future research, looking at like pivoting to Circle CI self-hosted runners if someone's using those, just by attacking those config YAML files, given a malicious, given a compromised personal access token. And a couple of the resources and references I used. Again, I really want to call out how good GitHub's API documentation and just general documentation is. Okay, and how it's been really helpful in putting together this talk. There's a self-hosted runners blog post that colleagues in Praetorian and I released back last summer, as well as our ShmooCon 2023 talk. And I want to call out this blog post from Kareem Rahal covering like reverse engineering the GitHub Actions runner and how it actually pulls secrets from GitHub. That was really helpful in developing some attack TTPs for dumping secrets given a compromised token. And I want to quick shout out my two colleagues at Praetorian, Mason and Matt. They were my co-presenters at ShmooCon and co-developers of the Gato tool. And I want to also thank John and Jimmy, also colleagues at Praetorian. They were the first to use Gato during that assessment where I covered that case where an infrastructure engineer pushed code and they were able to steal secrets. And that was the first like real world usage of that tool. And that led to demonstrating a pretty cool attack path. And all right, thank you so much for everyone's time. Glad to take any questions.
All right, if you've got questions, please raise your hand. I will come run to you with a microphone. First question is about middle height on your right.
Thank you. So you mentioned that in the pen tests you've done, you haven't seen organizations using ephemeral and isolated runners, but you did link out to a couple of tools that like help provide that functionality. So why do you think though you haven't seen those adopted in practice? Are those like really hard to use, or is it just an awareness problem?
So yeah, just to clarify, so we actually have seen ephemeral and self-hosted runners. However, they were not secured properly. And that, in one example, the service account it was running was over provisioned, so we then moved over to and privileged within AWS. So they had ephemeral runners, but they didn't provision them properly. So they use them, but we found issues.
Any other questions? I'm getting my steps in today for sure. No, you're good.
Hi, so you talked about, oh, I'm up here.
Okay, probably with the light, so.
Yeah, so I'm wondering what you think about using service accounts for personal access tokens, because, you know, people or developers can have their own personal access tokens that we can use for CI/CD builds, and I wonder what your thoughts are on using service accounts instead of developer accounts in the instance that a developer switches teams or, you know, leaves the company, that sort of thing.
Yeah, so in terms of, the question was using service account tokens instead of developers' own personal access tokens for, just to clarify, this is it for use in like secrets?
Use of secrets, yes.
Yeah, okay, yeah. So one way that would make it easier to secure and have more insight into what's happening is using those GitHub apps and having the app installation tokens being used for the actual operations. Those allow more fine-grained controls, and it's easier to monitor like which apps are installed. So you could have a GitHub app that's doing service and using GitHub apps as a service account, because in GitHub, when you have a service account, it's just another account. It's just like another user, and compromising a token associated with those is just as bad as compromising a developer.
We have time for one last question. If we have one last question from the audience. Raise your hand. Sorry, one more time. Oh, thank you. Coming down to you.
Did you wear your Fitbit today? I was wondering if you've explored any attack vectors with third-party actions, and if you have any recommendations on how to mitigate the risks there.
So not personally. However, I've definitely read some blog posts and other techniques like looking at vulnerabilities within third-party actions, and some of where those might come up is if you have a compromised token that doesn't say have the ability to modify a workflow, then you can't modify the YAML file and therefore have to look at vulnerabilities and how a third-party action used in a build is handling code that's in the repo that you can modify. Because if you compromise a token that has the workflow scope, it doesn't really matter what the other actions are doing because you can just edit the workflow itself and do whatever you want.
One last round of applause for Adnan, please.
Thank you so much, everyone.